Okay, so we're going to look at some code for the algorithm. The two examples we looked at was the location Cauchy example and the bridge regression example. And so in the location Cauchy, this is our favorite example to talk about in the one-dimensional case. We have the same data as we've had so far. So if I look at x, because I've set the seed, this is the exact same four observations. And then I have the same function that evaluates my log likelihood for a given value of mu. And then I evaluate that log likelihood and plot the negative log likelihood. Sorry, not negative, but the log likelihood of the function. And so what I'm going to do is I'm going to, so I'm not going to start, sorry, this is wrong. This is not Newton-Raphson. I'm going to starting the algorithm now. No, Raphson. The tolerance I've set is 10 to the power minus 5. Again, some of these are user chosen. I know that for the location Cauchy example, I do have the gradient involved, except the only thing that I don't have, which is different from the gradient ascent, is that the learning rate is actually being informed based on where I currently am, right? Or rather, the learning rate is being informed by the L, right? By the lower bound that I have constructed that is actually a universal lower bound. So F prime is definitely needed, F double prime is not needed. And I'm not going to choose a good starting value, I'm going to choose a bad starting value. So the starting value I'm going to choose is minus 10. The difference I set is 100, iter I set at 0. And remember, gradient ascent took a long time. So I'm going to make sure that I don't get stuck in a loop. So I set iter less than 1000. Now mu k is first current. I increase the iteration value. I update the mu k based on the math that I did, which is current minus f prime divided by minus 2n, which is exactly what the iteration based on the algorithm was. I store my mu k's because that's what I want to plot. And if the difference of the update is small, then I want to stop doing this process. Okay. And I run that, and the value it converges to is 4.56, and number of iterations took 138. So that is certainly faster than gradient ascent for many choices of the learning rate, but not as fast as Newton-Raphson. And I can plot this and see we started a really bad starting value, but we converged to the actual solution here as well. Now I can change the starting value to, let's say, 40. Okay. And I can see that the number of iterations it takes is 480, and then eventually, because algorithm is guaranteed to climb my objective function, it has the ascent property, so we'll keep going little by little to the actual increase, but it will go to a local maximum. I can start at 7, which is what I started in the location Cauchy problem. And when I start at 7, in 17 steps, beautifully, it goes slowly up, does not go on the other side. Now it can go on the other side as long as it climbs the objective function. So it could jump from here to here and then here and here. So it could oscillate, but every time, even if it oscillates, it has to climb the function. Okay. I can also start at, let's say, 15 maybe. And when I start at 15, I go to this side of the local maxima. So naturally, the global maxima is not guaranteed if you have a non-concave objective function, but it will certainly go to a local maxima and will always have the ascent property. That's the really nice thing about this one. Okay, that is the location Cauchy implementation. We'll also look at the bridge regression implementation. So the first thing I wanted to do was, what I'm going to do is I'm going to generate my data. So I set the seed, I get 100 observations, I set P to be equal to 5, and the actual regression coefficients to be equal to 0, 0, 0, and then two randomly chosen numbers. So the beta dot star, or the actual regression coefficients, are 0, 0, 0, minus 0.6, and 0.18. Then I'm going to just casually generate data, generate my x's, which is cbind 1 comma my matrix of randomly chosen observations. So the first column is going to be my, so let me just reduce this. The first column is going to be my vector of 1. So if I do head of x, I get a vector of 1s and then randomly chosen observations from a normal distribution. But I'm going to use the linear regression model to generate my response, y equals x beta plus epsilon. So if I do head of y, these are my observations for the response variable. Now, what I'm going to do in this particular implementation is we will implement MLE, ridge regression, and bridge regression for different values of alpha. This is our goal, right? And I know when alpha equals 1, this is lasso regression. And I know that when alpha equals 2, we have ridge regression. And anything between is all valid within this regression paradigm. So first, I know I can do the MLE. The maximum likelihood estimate, in fact, in this case is available to me because X transpose X is invertible. So I calculate that and beta dot MLE looks something like this, right? We have that tractably. We don't need any sophisticated optimization tools. The solution is available to us. And now I'm going to consider the following bridge regressions. I'll do 3 different bridge regressions. Alpha equals 1, alpha equals 1.5, and alpha equals 1.8. I'll also do ridge regression later on, which is alpha equals 2, but I'll do it separate. I fix lambda to be equal to 10. So my penalty parameter is 10. Okay. And so let me just increase this now. And what I'm going to do is I'm going to collect all the regression coefficients I get using the three different bridge regression methods. So I create a zero matrix where the number of rows are P and the number of columns are the number of alphas I'm looking at. Right? So this is going to give me all bridge regression estimates for the 3 different values of alpha. And I will require a numerical optimization technique, algorithm for this. So for my epsilon tolerance is 10 to the power minus 5. Now, what I'm going to do is I am going to start at the ridge solution. So for each alpha value, I'm going to go and run a loop that finds the bridge regression estimates for that alpha value. So inside each loop is an algorithm implementation that finds the bridge regression estimate for that value of alpha. Okay. So within this value of alpha, the first value of alpha is just 1. That means it's lasso. Now, where should I start? I don't want to start at the MLE because I know that the ridge is already a penalized estimate. So why not start with the ridge solution? And the ridge solution I know is X transpose X plus lambda IP, so that's disturb, inverse, so that's solve, times X transpose Y. So this is the ridge solution. I start from there. I make my iters to 0. I do my diff. I want to make sure that iters does converge or doesn't get stuck in a large loop. So iter is iter plus 1. I create my M matrix. So remember, my iteration update is the following, right? So my iteration update is beta k plus 1 is equal to X transpose X plus lambda mk inverse X transpose Y, right? This is what I need to do. And so this mk over here, according to my theory, is a diagonal matrix with elements small m I comma k by alpha. Where what is small m I comma k? Where small m I comma k is nothing but alpha times absolute value of beta I comma k, I think. to the alpha minus 2, to the alpha minus 2. Okay, so this is just to remind you, you can go back and look at the notes or the previous video, but this is just to remind you what MIK looks like. So what I'm going to do is I'm going to find the diagonals of this M matrix, which is I'm going to obtain the vector of small m's. So this is as dot vector, and also there's a lambda by 2 times, I think there's, is there a lambda by 2? Yes, okay. So there's a lambda by 2 embedded here. So I'm actually calculating all of these things together over here. And actually, I think this is a typo. This should be lambda by alpha, not by lambda by 2. So it's lambda dot alpha vec I. Okay, now this is correct. MIK is by alpha, so that is correct. And then MIK is, yeah, I believe this is correct. Or actually, let me just leave it at 2. And if it's incorrect, we might discuss it at a later point. Okay, coming back to this. So MS is as dot vector lambda by 2 absolute value of current, which is beta IK, to the power alpha minus 2. Now, which value of alpha? Well, I'm doing this for multiple values of alpha, so I do alpha dot vec at the ith position. So it's the current value of alpha I'm looking at. I'm just going to say that just go back and check the formula of whether this is by 2 or it should be by alpha, or there's some other, maybe something else, maybe a small error here. I know this code should work, but there might be a small error here, so please verify that on my behalf. Okay, so the updated value now is just going to be x transpose x plus lambda diagonal of ms inverse x transpose y, right? And because I've taken the lambda inside, that's why it's not over here. Now, how do I check whether I have converged close enough to the actual optima or not? We don't have gradients at our disposal in this example. So what I do is I check the size or norm of the update. Right? So I take square root of the sum of current minus update whole squared. So I check the size or the norm of the update in diff. And if diff is greater than tolerance, then I stop, then I continue as long as it's greater than tolerance. As soon as it's less than tolerance, that's when I stop. Okay. And once it finishes, it's going to print I, as in which alpha have I done? What is my iter? So how many iterations did it took to converge? And this is just to see if it maxed out for any particular choice of alpha. And then once it's actually converged, I'm going to take my current iter, the last iteration, and going to put it in the ith column of beta dot bridge. Okay, so we've set everything up. Let's actually run this. And when I run this, I see, okay, for the first value of alpha, which was 1, it took 15 iterations to converge. The second value of alpha, 4 iterations. Third value of alpha, 3 iterations. And this is not surprising. We're starting at the ridge solution, which is alpha equals 2. And alpha equals 1 is the farthest away I can go from alpha equals 2 for the allowable values of alpha. So alpha equals 1 takes the largest number of iterations. Alpha equals 1.5 is a little less, and alpha equals 1.8, even less so. I also look at the ridge solution, which I know what I already calculated once, but I save it here again. And then now what I'm just going to do is I'm going to create a matrix of the MLE estimates, the bridge regression estimates, the ridge regression estimates, and the actual beta dot star that I use to generate my data, because that I have the luxury of having that at my disposal. Okay, I do that, I give it column names, and then I look at the estimates. So what do we see? The truths are 0, 0, 0, minus 0.6, minus 0.18. The MLE is, this. For example, here minus 0.6 is fairly close to minus 0.6 here. 0.2 is fairly close to 0.18. This is fairly close to 0, but these two are not. Okay, but as I'm going to decrease the value of alpha. So if I go alpha equals 2, alpha equals 1.8, 1.51, I'm going to see values being pushed closer and closer to 0. Okay? So over here, I get minus 0.08. Over here, I have minus 0.03. And there is a gradient over here so that it gets closer and closer to 0. I'm at 0.2 at MLE. Then when alpha is 2, I'm at 0.17. Then as alpha is decreasing, I'm typically going to see over here something small happens, but I'm going to see closer and closer convergence to 0, towards 0. Here also I see movement towards 0. Here also I see movement a little bit, not that much, but a little bit movement towards 0. Here also I see a little bit movement towards 0. Okay, because it's going to push estimates towards 0 or shrink them, because it's been the penalty term, smaller values of alpha are more aggressively penalizing my solution. But what we see is that the algorithm is able to converge to these estimates without actually having to calculate them, without actually having to calculate the gradient. So what I would like you to do in this code is change the value of lambda and see how things work for different values of lambda. I would also like you to verify, make sure that the actual steps in the code make sense. So please go ahead and do that as well. And see what happens if you change the starting values of beta from the ridge solution to something else. Okay, so I would encourage you to play around with this code and see what you get.